Hello and welcome. This is going to be a video on air navigation. Feel free to pause the video at any point to record the notes and examples in your notebook. Let's get started. To begin, air navigation is different than how we've been measuring angles in many ways, where we have started with 0 along the positive x-axis. With this, the 0 degrees will be measured from true north. As we go around, it is not counterclockwise, but the directions go clockwise. So 90 degrees is actually east. 180 degrees is the measurement for south. 270 degrees is west, and a full 360 degrees is back to north. And the other subsets of directions that you may want to be familiar with are at the 45-degree angles, like northeast, southeast, southwest, and northwest. So make sure you note that when you have words that describe things as east or west or southeast, that those are describing these perfect angle numbers, 45, 90, and so on. Let's continue. So what's going to happen here in these problems? Well, to begin, we are going to have a situation where we are starting a plane at an airport, but we're going to be looking at it from a bird's eye view. So there's our location. And remember, north is always the direction going up here. So we have our plane, and we want to go in this general direction over here. And ideally, that's where we would go. That would be our heading, and that's where we would end up. But there's a factor here that's going to affect this, which is the wind. And so the wind is going to have an effect on where our plane travels. And so those vectors there are going to cause the wind to shift. And so the wind is going to make the plane, instead of go right on the green line where it was aimed, you can see that it would travel over here on this red line, which is the resultant. And so we will be adding these vectors together to figure out where this plane actually ended up on its course. And so some of the words here that you need to be familiar with, as we've mentioned before, air navigation is always measured from true north. That is not a vector of measurement, but it is just a way to describe your direction. The word heading is the direction the plane is pointed or where it wanted to go. The course is the direction that the plane actually moves over the ground. That is after the effect of the wind. Airspeed is the speed relative to the air, what the plane thinks it's doing. And the ground speed is relative to the ground. That's after the fact of wind. So if the wind is pushing behind it, maybe the ground speed is making the plane travel faster than it was intending to. Or if the wind is in its face, maybe it's making the plane fly slower than it actually was intending to. These here are the magnitudes and directions of each vector. I'll try to color code them here. As you can see, airspeed and heading are set. The magnitude is the airspeed, the direction would be the heading. Wind speed is the magnitude with the wind direction, and ground speed is the course. And so in general, this is what we're going to have, is measuring from our direction. We want to have a heading going where we want it to go. The wind is going to cause that to go somewhere off of where we were aimed, and that'll cause the course. And so the heading plus the wind direction is our course. Let's look at this first example here. The plane is heading northeast, which is that perfect 45-degree bearing, at an airspeed of 500 miles per hour. The wind is blowing from the southeast at 315. Now, southeast, pay attention to the word from. So it's really going towards the northwest, and that's why it's 315 degrees. The speed of that is 75 miles per hour. We want to find something called the drift angle, which we'll talk about in a moment here, the ground speed, and the course of the plane. So drawing my north arrow here, I want to have a 45-degree angle of 500 miles per hour. The wind is 75 miles per hour going to the northwest, again, coming from the southeast. But I can't add those vectors as they are, so I need to move that vector to the end of where my heading is, and so I can see that the resultant is actually where the plane ends up flying. And so because of the angles that are given, 315, 45 degrees, we actually do have a right angle in this problem. And so I can use Pythagorean theorem as a way to find our magnitude, which would be the ground speed of that red vector. And so the ground speed in this calculates out to be about 505.6 miles per hour. Since it is a right triangle, I can do many different things to find the angles involved in this. And so the one angle that we need to talk about is something called a drift angle, which I'm denoting here as alpha. And so that angle is this distance here between the red and the green vector. How far did it drift off of its original heading? And so I can use inverse tan as a way of calculating that. And so that angle there is about 8.53 degrees, which means instead of heading at the 45, which is where we thought we were going, we are actually going more towards the north. And so the course that the plane actually flies on is 45 minus 8.53, which is 36.47 degrees. And so that is the course that the plane actually flew on. Let's take a look at one more example here, which is a plane that is heading on a bearing of 250 degrees with an airspeed of 425 miles per hour. The course has a bearing of 262 degrees. The ground speed is 475 miles per hour. Again, we will find the drift angle, the wind speed, and the wind direction. So this is a little bit different since we are given where we are starting and where we are ending. We want to find the wind, which is causing the effect of that. So drawing this out, measuring from north, I have a direction of 250 degrees, so sort of southwest at 425 miles per hour. It ends up going at 475 miles per hour, again, kind of to the southwest, a little bit almost to the west exactly, 262, but not quite 270. And so the effect of that is being caused by that wind, which is that blue vector there, which I'm just going to call x in this problem. So the easiest thing to find first is the drift angle, because we know we were starting at 250 degrees, and now we are ending up at 262. And so to calculate that, we can just simply subtract the difference, and that is how far we drifted, 12 degrees. Using law of cosines, I can figure out my wind speed, which is the magnitude of that. And so that turns out to be a wind speed of 106.41 miles per hour. And so now I know the length of that. The direction angle, though, will be a little bit different because, again, remember, we can find angles within this triangle, but we always need to measure things from true north. So I'm going to create a parallel vector of wind over back at the beginning of this problem at the north arrow. And I know that the angle from the north to the red is a total of 262 degrees. So if I can just find this missing angle between the red and the blue, which I'm going to call beta, then I can add that beta value to 262 to find the direction of my wind. Now the beta right there is not inside the triangle, but there is a beta within my triangle that is equivalent. And it's also located between the blue and the red vectors, which is over here, because those are alternate interior angles. And so now I can set up a law of sines problem to find my wind direction. I'll find my beta value, which turns out to be about 56.14 degrees, but that's not the angle. That's just the distance of the value of beta, excuse me. And if I add that beta value to the 262, I can find the actual direction of the wind. So I hope that helps. I hope that explains some of the concepts here of air navigation. Thank you.